Okay, welcome back. We were talking about the VC dimension for various hypothesis sets, and because, as we shall see going forward, the VC dimension and VC analysis as such, right, plays a significant role. It's really worthwhile to try and gain some insights about the VC dimension before we actually try looking at the generalization bound again. So one way to gain insight is to look at some familiar learning models, and Perceptron is one of them. So let's begin with the Perceptron. Okay, so the way the Perceptron was formalized earlier is that you're essentially looking at the sign of W transpose X, which kind of tells us that in a d-dimensional space, so if this is d-dimensional, we have how many parameters, like W0, of course, W1, and so on up to WD, which means D plus 1 parameters. Okay, so let me state this theorem for the perceptron, and this is particularly useful because we'll be working with the perceptron a lot. So the theorem states that the VC dimension of the perceptron, and let me write it, perceptron is D plus 1. Okay, so this is indeed a very useful result because if you look at it, it's quite small, right? And it's a good result because you have a d-dimension, like you mostly will be working with d-dimensional data, and you have at least these many dimensions to work with. And Perceptron achieves this D plus 1 complexity. Just a reminder quickly. So how is this important to us? It's important to us because of this link, and I'm like just writing the order of this complexity here, which is somewhat dvc log of n over n. It's a quick reminder. Okay, so Perceptron, as you can see, is one of the most fundamental models, and all linear models, including neural networks, are built on the Perceptron, right? So this is one of the fundamental models, and that's why this theorem is so important to us, because this is, if you look at it, a good result, right? Now, of course, this is a theorem, and we need to prove it, right? So how do we prove that the VC dimension of a perceptron is exactly D plus 1? Now, I'm not going to show you the entire proof here because this is, I think if I remember correctly, this is exercise 2.4 in the book. And it's, I think, a homework problem as well. But I can give you some idea of like how to go about doing this proof. So basically, the proof can be divided into two parts. The first part is going to be that you can show that the VC dimension for the perceptron is greater than or equal to D plus 1, right? And the second part could be to show that the VC dimension for the perceptron is less than equal to D plus 1. And mathematically speaking, if we combine both these results, you can definitely conclude this here. Right, so you will be able to conclude that the VC dimension of a perceptron is D plus 1. And just a quick reminder, what is a VC dimension? If we forgot, the max number of data points that you can shatter, right? So max number of data points you can shatter. Okay. So how can we prove each of these? So for the first one, if you think about it, the first part, when we are trying to show that the VC dimension is greater than or equal to D plus 1, we can show that the maximum number of data points you can shatter in like a perceptron can shatter is at least D plus 1. Okay, so basically it will be enough to show that you can shatter a single collection of D plus 1 points or some collection of D plus 1 points. And this like hypothesis set can shatter this particular collection of D plus 1 points essentially. So that's like any D plus 1 points. So that's the first part. The second part is slightly tricky. So basically here, you're trying to show that the VC dimension is less than or equal to d plus 1 points, right? So what exactly am I trying to show? What happens if I have like d plus 2 points? So if you're able to show that every set of d plus 2 points cannot be shattered, no matter how you arrange those points, I think that is enough, right? So a lot of like linear algebra might go in proving that. And the book provides some hints on how to do that. For example, the input, like each point in X is a vector of length d plus 1. So we can use the fact that d plus 2 vectors of length d plus 1 must be linearly dependent. And this is assuming that you have a non-singular d plus 1 times d plus 1 matrix. And its rows represent d plus 1 points, right? So that's a small hint. And that hint actually appears in the textbook as well. But basically what you'll be showing in this part is that in d plus 2 points, you can construct a dichotomy that is non-implementable, right? So maybe focusing on d plus 2 points in this particular part. And as I said, this one gets more trickier than the first one. So combining these two, you'll be able to prove that the perceptron has the VC dimension exactly equal to d plus 1, which is really, really good. It's a good result, as I said, for any hypothesis set. And that kind of like explains why we use the perceptron so much. Okay, so that's about the perceptron. Now let's go and start talking about something that's known as the approximation versus generalization trade-off, which is kind of the heart of machine learning analysis anywhere. And basically what we are trying to do here is we are looking at the practical implications of approximation versus generalization. Okay, so let me write it down. Approximation versus generalization. In like there is another sort of version of this. It's also known as the bias variance trade-off. More from the statistical perspective of things, it's also known as the bias variance trade-off. And of course, we'll see how this is bias versus this is variance. Okay, so if you remember, again, like of course we remember, let me just like rewrite this equation, the relationship between E out of G versus E in of G with this error bar, of course, which we also call complexity going forward. So 8 over n log of 4, log 4, and then there was this 2n dvc. I think there was a plus here over delta. Now this is the error bar, right? Inside this bar is the actual approximation versus generalization. This entire thing is essentially when we can denote it by omega, and this is a function of the VC dimension and the number of data points that we're working with. And this is also of the order, and this again is a known result now, a log of n over n. Okay, so as I said, this actually represents the approximation versus generalization. Let's look at it in a picture or in a graph. So let us assume this is my error, and let us assume this is my complexity, and complexity going forward will now be denoted by the VC dimension, because this is like the complexity of my hypothesis set measured by my VC dimension, right? So it's quite evident that my my in sample error goes down as I keep increasing my VC dimension, right? So this is approximating. Why? Because I get more choices as my complexity goes up, right? And so this is approximation, right? I'm trying to approximate. Okay, how about the generalization? So I know that the complexity representation is this. This is my complexity, right? And like if I go in and try to graph it, this is what omega represents, and given n is fixed, also that. So if n is fixed, this is my model complexity, and if we combine both of them, I get something like this, such that I have like some minimum value here, which I call the optimal VC dimension here. right? So basically what we're trying to do is we want to get a small e in, right? But we also want this link. This should be small, of course. We all agree to that. But we also want this link to be maintained, right? And in order for that link to be maintained, I also need my complexity to be somewhat small, right? So this is exactly the trade-off that occurs between approximation and generalization, because this is where you're trying to generalize, right? So this is my generalization, right? So we want omega to be small. We also want en to be small. The only way out is that we, like, they're in opposite directions, right? So we create this like trade-off, and that trade-off leads us to this VC dimension having some optimal value. Okay, so this is the pictorial representation of an approximation generalization trade-off. Let's move on to two aspects of practice that are linked with this approximation generalization trade-off, and I'm going to continue discussing that in the next video.